Okay, so this and next question are related somewhat. So we'll do them together. Well, they're related in that they both deal with the entropy. So in both the questions, I believe we have to use this expression for change of entropy. The change of entropy for reversible processes, this is important, for reversible processes, is the transfer of heat divided by temperature. And in fact, in this question, I think that's it. It's pretty simple. So, you got 9 grams of steam that's going to be condensing to water. Okay, so entropy is going to be going down. So, so here for this question, the transfer of heat, it's easy. Latent heat of vaporization, the absolute value anyway, is latent heat of vaporization times the amount, mass. So I do need latent heat of vaporization. Wonder if I can do this in Wolfram alpha. Latent heat of vaporization of water times amount of steam, 9 grams. If Wolfram alpha can do it, then great. 20.1 kilojoule. And it's happening at 100 degrees C. So we divide it by, I guess I can just do that in my head. So it's gonna be 2.01 kilojoule per Kelvin, or 2010 joule per Kelvin. Oops, there's a minus sign there. Because again, the entropy is decreasing. Wait, did I miss something? Oh, this is why. The T it shouldn't be 100 degrees C. Let me see what Wolfram alpha does. So if I divided this by 100 degrees C, what will it do? It should really convert that to Kelvin, because this formula is only meaningful with the absolute temperature scale. That won't work. But I think, did they convert to Kelvin on its own? No, let's just do it properly. 373 Kelvin. So that calculation I can't do in my head. So doing that properly is seemed small to me, but so that's 53.8 joule per Kelvin. 53.8 joule per Kelvin. So okay, so I fixed the issue in the question, so now this answer should be accepted as correct. It was a little bit too tight of a tolerance. From 1% to, so I put it at 3%, so that someone using Wolfram alpha, like I usually recommend, will get an answer that the system will grade as being correct. Because this, even though it looked too small to me, it is correct, so it should have been graded as correct. Good. So let me go to the next question, and I'll be using some of the same stuff. The next question, it's a little bit more involved because it's got 2 different processes. So I guess it's probably good to draw that kind of phase. Let's draw this graph, a version of which you have seen in the textbook. So it looks like, I guess it's plotted as amount of heat transferred as a function of temperature. So water, starts out as ice, heated, starts melting. So this would be at 0 degrees C, and then it's heated again, and then it starts to boil. So this would be 100 degrees C, and then eventually it all boils, and then vapor increases in temperature. So in this question, you are starting out as somewhere here at what your textbook question is saying, 29 degrees C. You are starting out as somewhere here, and you are adding heat until the point where it completely all evaporates. Now, this part of the calculation, it's easy. We can just do this the same way we've done. In fact, so let's do that. So I'll just write out the part that, so let me call this part B. And I'll just write out the thing that I'll add on after we are done with the other part that's going to be longer. So delta SB should be so the latent heat of vaporization times the amount of water, 41 grams, divided by the temperature, 373 Kelvin for the temperature at which it's boiling. So we'll be adding this on after we are done with part A of the process. So part A of the process is more complicated because for this to be a reversible process, as the water temperature changes from 29 to 100 degrees, you have to imagine reversible heat transfer, meaning heat transfer happens at the temperature of the water. So this T here, which was constant in our question so far, is now going to be a variable. So I really have to write out this version of the expression first. The infinitesimal amount of the entropy change for reversible process is the infinitesimal amount of heat transfer at a given temperature. And for a total, so what I would call total entropy change for process A, it should be integral of this process. Now I have to express dq in terms of temperature. I can do that for this part of the process here by saying the infinitesimal amount of heat transferred is amount of mass times specific heat capacity times the change of temperature. So m times c times dt over t going from initial to final. So this will give us the change of entropy in process A. So let me quickly do this integral. That's 1 over x, so it's gonna be natural log m times c. Evaluated the two limits. I'm just gonna do the logarithm algebra in my head. That'll be natural log of t final over T initial, and I'll be careful to express these in absolute temperature terms. So let's work this out. So for A, it's gonna be the specific heat capacity of water times the 41 grams times natural log of the final temperature, 373 Kelvin, boiling temperature of water, divided by initial temperature, 29 degrees C, which is adding 273, that's 302 Kelvin. Yeah. So that is the entropy change, I think, for part A. Let's see if I get the quantity in the unit of joules per Kelvin. Oh, wait, what? It couldn't do specific heat capacity of... So let's just look up the constant looked up from the textbook, because we kind of need that anyway. So water is 4 point something, right? Oh wait, I need a different table for that. 4 point, do I have it memorized? 4.1 something, but I think I've forgotten enough of it that I shouldn't rely on my memory just to look up the thing that I have. Water in liquid form, 4.4186 joules per kilogram. Yeah, so for per gram, it would be 4.186. So 4.186 joule per gram. I think per Kelvin, I think. Yeah. So this is so far in the wrong. Per gram times Kelvin. Okay. So there's entropy change of this amount, 36.239 joule per Kelvin. And now I have to add in the entropy change in part B. So that's gonna be plus the let's use the number from the textbook, and I'll review the precision of the thing later. So the number from the textbook is heat of vaporization 2256. That's kilojoule per kilogram. So 2256 joule per gram. 2256 joule per gram. Same amount of grams times 41 grams. Divide by 373 Kelvin. So the entire thing, did it interpret me correctly? Yeah. 284.2 joule per Kelvin. 284.2 joule per Kelvin. Yeah, that's it. So those are the two questions, again, related to each other. Sorry for the delays in tracking some of the issues, and I'll review this question and make sure it doesn't have too tight a tolerance. And yeah, so this is it. I think that actually finishes the entire problem set. So thank you, and I'll see you next time. Bye.